Welcome to World Storyguide. Today we're going to talk about one of the most transformative and fascinating journeys in human history, the story of artificial intelligence. From ancient myths of mechanical beings to the age of machines that learn, create, and reason, this is a story about humanity's oldest dream, building a mind. Sit back, relax, and let's begin. Chapter 1: The Dream Before the Machine. Long before there were computers, before electricity, before the Industrial Revolution, humans were already dreaming of artificial life. In ancient Greece, the god Hephaestus, the divine blacksmith, was said to have crafted golden maidens from metal, mechanical servants who could speak and assist him in his forge. There was also Talos, a giant bronze automaton created to protect the island of Crete, walking its shores 3 times a day, guarding against invaders. These were myths, of course, but they reveal something profound. The idea of artificial thinking beings has lived in the human imagination for thousands of years. Fast forward to the Renaissance, and we find Leonardo da Vinci sketching mechanical knights, armored robots that could move their arms and sit upright. They were never fully built, but the vision was there. In the 17th century, French philosopher René Descartes proposed a radical idea that animals were nothing more than biological machines, operating by mechanical laws. If an animal could be a machine, he wondered, could a machine become an animal? By the 19th century, the idea began to take on real scientific weight. In 1843, Ada Lovelace, a mathematician and the daughter of poet Lord Byron, wrote notes on Charles Babbage's analytical engine, a mechanical computing device. In those notes, she described something extraordinary for her time: the possibility that such a machine could be programmed to do far more than simple arithmetic. She imagined it composing music, playing chess, doing science. She wrote that the engine had no power of originating anything. It could only do what we know how to order it to perform. That caveat would echo through AI history for over a century. Part 2: The Birth of a Science. The 1940s and 1950s. The 20th century arrived, and with it, electricity, electronics, and the first true computing machines. During World War II, a brilliant and deeply unconventional British mathematician named Alan Turing worked at Bletchley Park, cracking Nazi Germany's Enigma code. But Turing's mind was always racing ahead. He wasn't just thinking about decoding messages. He was thinking about the nature of intelligence itself. In 1950, Turing published one of the most important papers in the history of science: Computing Machinery and Intelligence. It opened with a deceptively simple question: can machines think? Rather than answer that philosophically impossible question directly, Turing proposed a practical test. Imagine, he said, a person sitting at a terminal having a text conversation with two entities, one human, one machine. If the person cannot reliably tell which is which, then the machine has demonstrated something we might call intelligence. This became known as the Turing test, and it shaped how people thought about AI for decades. Turing wasn't alone. Across the Atlantic, Norbert Wiener was developing the field of cybernetics, the study of systems that regulate themselves through feedback. He argued that brains and machines operated on similar principles. John von Neumann, one of the greatest mathematicians of the 20th century, was designing computer architectures that are still the basis of nearly every computer today. And Claude Shannon, working at Bell Labs, was laying the foundations of information theory, the mathematical language of data and communication. The pieces were assembling. What was needed now was a spark. That spark came in the summer of 1956. Part 3. Dartmouth. The summer. Everything began. Picture a small college town in New Hampshire. It is the summer of 1956. A group of mathematicians, psychologists, and computer scientists have gathered at Dartmouth College for a 2-month workshop. The organizers, John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, have written a proposal with an ambitious premise. They believe that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. And they gave this new field of inquiry a name: artificial intelligence. The Dartmouth Conference is considered the official birth of AI as a scientific discipline. John McCarthy, the host, was a visionary who would go on to create Lisp, one of the earliest and most influential programming languages, and the dominant language of AI research for decades. Marvin Minsky, perhaps the most charismatic of the group, would go on to found the MIT AI laboratory and write books and papers that shaped how the world thought about minds and machines. The mood at Dartmouth was electric. The attendees genuinely believed they were on the verge of creating human-level artificial intelligence. Some thought it would take just a few years, a decade at most. They were wildly optimistic, but that optimism drove extraordinary early progress. Part 4. The Golden Age of AI and the First Winter. Through the late 1950s and into the 1960s, AI researchers produced a remarkable series of achievements. In 1956, Arthur Samuel created a checkers-playing program that could learn from its own games and improve over time. It was one of the first demonstrations of what we now call machine learning. In 1959, Herbert Gelernter built a geometry theorem-proving machine. Alan Newell and Herbert Simon created the General Problem Solver, a program designed to mimic human problem-solving heuristics. Then, in 1966, Joseph Weizenbaum at MIT created ELIZA, a simple chatbot that could simulate conversation by pattern-matching user inputs to scripted responses. ELIZA's most famous script, Doctor, mimicked a Rogerian psychotherapist. It would respond to "I am unhappy" with "How long have you been unhappy?" Users were astonished. Some formed emotional attachments to it. Weizenbaum himself was disturbed by how readily people anthropomorphized the program. He wrote a book warning about the dangers of attributing human qualities to machines. But behind the enthusiasm, there were deep and unresolved problems. Early AI systems were brittle. They worked well in narrow, well-defined domains, but collapsed entirely when faced with real-world complexity. Translating languages turned out to be far harder than anyone expected. Not just a matter of swapping words, but of understanding context, culture, and ambiguity. Robotics was confoundingly difficult. Computers were also slow and enormously expensive. By the mid-1970s, funding began to dry up. In Britain, the Lighthill Report of 1973 savaged AI research as overpromising and underdelivering. The US government cut funding sharply. The field entered what historians would later call the first AI winter, a period of reduced expectations, diminished funding, and widespread skepticism. It would not be the last. Part 5. Expert Systems and the Second Wave, the 1980s. AI did not die in the winter. It went indoors, into the corporate world. In the 1980s, a new approach emerged: expert systems. Rather than trying to create general intelligence, researchers asked, can we encode the knowledge of a human expert into a set of rules that a computer can apply? The answer was yes, and businesses loved it. Mycin, developed at Stanford in the early 1970s, could diagnose bacterial infections and recommend antibiotics as accurately as a human physician. XCon, developed for Digital Equipment Corporation, configured computer systems and saved the company an estimated $40 million a year. Companies rushed to build expert systems for finance, medicine, law, and engineering. The commercial AI industry exploded. By 1985, American and European companies were spending over $1 billion a year on AI hardware and software. Japan launched its ambitious fifth-generation computer project, aiming to build AI-powered machines that would leapfrog Western technology. The US and Britain responded with their own national AI initiatives. But once again, the promises outran reality. Expert systems were expensive to build, and even more expensive to maintain. The rules had to be handcrafted by programmers working with domain experts. A slow, painstaking process. And when reality didn't match the rules, when an edge case appeared that no one had anticipated, the systems failed catastrophically. They had no ability to learn or adapt. By the late 1980s and early 1990s, the expert systems market had collapsed. Companies that had bet big on AI wrote off their investments. The field entered its second AI winter. Part 6: The Quiet Revolution. Neural networks and the 1990s. While expert systems were booming and then busting, a quieter revolution was underway. Back in the 1950s and 60s, researchers had been inspired by the biology of the brain. The brain, after all, is the only proven example of general intelligence we know of. It works not through explicit rules, but through billions of interconnected neurons, each sending tiny electrical signals to its neighbors, adjusting the strength of connections based on experience. Could computers simulate this? Frank Rosenblatt thought so. In 1958, he built the perceptron, a machine that could learn to classify simple images. It generated enormous excitement until Minsky and Papert published a 1969 book showing that a single-layer perceptron could not solve certain basic problems. Funding dried up, and neural network research went dormant for over a decade. But in the 1980s, researchers discovered a breakthrough: backpropagation. This algorithm allowed multi-layer neural networks to learn from their mistakes, adjusting the strength of connections throughout the network based on errors. Geoffrey Hinton at Carnegie Mellon, David Rummelhart, and Ronald Williams published the landmark 1986 paper that brought backpropagation to mainstream attention. Neural networks could now learn to recognize patterns, classify data, even predict sequences. Progress was still slow. Computers weren't powerful enough. Data was scarce. Neural networks sat in the shadow of more fashionable approaches. But in 1997, the world got a glimpse of what was coming. IBM's Deep Blue chess computer defeated the reigning world champion, Garry Kasparov, in a 6-game match. The world was stunned. Chess had always been considered the ultimate test of human intellectual superiority. Now a machine had beaten the best human player alive. Kasparov was furious. He alleged that IBM had cheated, that human grandmasters had intervened during the match. IBM denied it. Whether or not the controversy was justified, the world had witnessed something historic. machines could compete with and defeat the greatest human minds in games of pure strategic reasoning. Part 7: The Big Data Era and the Deep Learning Revolution, 2000s and 2010s. The 2000s brought two forces that would change everything: the internet and cheap computing. The internet was generating data at an unprecedented scale. Every search query, every click, every purchase, every social media post was a data point, and there were billions of them. For the first time, AI researchers had access to truly massive data sets. At the same time, graphics processing units, GPUs, originally designed for rendering video game graphics, turned out to be extraordinarily good at the kind of parallel mathematical operations that neural networks require. What once took weeks to compute now took hours. What took hours took minutes. In 2006, Jeffrey Hinton and his collaborators published a paper showing that deep neural networks, networks with many layers, could be trained effectively if you initialize the weights carefully. This sparked what became known as the deep learning revolution. The results were dramatic. In 2012, a deep neural network called AlexNet, developed by Hinton student Alex Krzyzewski, entered the ImageNet competition, a challenge to classify 1 million images into 1,000 categories. AlexNet didn't just win. It crushed the competition, achieving an error rate dramatically lower than any previous system. The computer vision community was shaken. Within a year, nearly every team had switched to deep learning. The floodgates opened. Deep learning transformed speech recognition. It transformed language translation. It transformed medical imaging, detecting cancers in X-rays with accuracy matching or exceeding radiologists. It transformed autonomous vehicles. It transformed fraud detection, drug discovery, music recommendation. Google, Facebook, Microsoft, Amazon, Baidu. Every major tech company poured resources into deep learning. Universities launched AI programs. Startups multiplied. AI research papers went from hundreds a year to tens of thousands. Then came a moment that stopped the world. Part 8: AlphaGo and the Game of Go. March 2016. Seoul, South Korea. A packed auditorium. Millions watching online. The Game of Go, an ancient Chinese board game of extraordinary complexity, had long been considered the last great bastion of human intellectual dominance over machines. Chess has roughly 10 to the power of 47 possible game states. Go has 10 to the power of 170. The search space is so vast that brute force computation is essentially useless. Human Go masters rely on intuition, pattern recognition, and something that feels almost aesthetic: a sense of beauty in the placement of stones. Google DeepMind's AlphaGo had been trained on millions of human games, and then had played millions more games against itself, learning strategies that no human had ever conceived. Lee Sedol, one of the greatest Go players in history, 9-time world champion, was its opponent. AlphaGo won 4 games to 1. Move 37 of Game 2 became famous worldwide. It was a move that human commentators initially called a mistake. No professional player would have made it. But it was not a mistake. It was a masterstroke that AlphaGo had calculated to be superior to any human strategy. The commentators fell silent. Lee Sedol left the room briefly, reportedly overwhelmed. In an interview after the match, Lee Sedol said something that stayed with many people. He said that AlphaGo had shown him moves he had never thought of. that it had expanded his understanding of the game. It was a humbling admission, and a profound one. A year later, DeepMind released AlphaGo Zero, a version trained with no human game data whatsoever. Starting from nothing but the rules of Go, it played against itself and within 40 days had surpassed all previous versions. It was, in a very real sense, an AI that had transcended human knowledge. Ha!
Part 9. The Age of Language. GPT, ChatGPT, and the Transformer Revolution.
For all of AI's advances in vision and games, language remained a stubborn frontier. Human language is not just a sequence of words. It is layered with context, implication, irony, metaphor, cultural reference, and emotion. Understanding a simple sentence like, "The bank was steep," requires knowing whether we are talking about a riverbank or a financial institution. And that depends on everything that came before. In 2017, a team at Google Brain published a paper titled, "Attention is All You Need." It introduced a new neural network architecture called the transformer. The key innovation was a mechanism called self-attention, a way for the network to weigh the importance of every word in a sentence relative to every other word, regardless of distance. The results were remarkable. Transformers outperformed previous approaches on language tasks by a wide margin. OpenAI, a research organization founded in 2015 by Elon Musk, Sam Altman, and others, seized on the transformer architecture. In 2018, they released GPT, the generative pre-trained transformer. It had been trained on a vast corpus of internet text. In 2019 came GPT-2, which was so surprisingly capable at generating coherent prose that OpenAI initially withheld the full model, fearing misuse. In 2020 came GPT-3, with 175 billion parameters, trained on hundreds of gigabytes of text. GPT-3 could write news articles, answer questions, translate languages, write code, compose poetry, and carry on conversations, all from a simple prompt. It wasn't perfect. It hallucinated facts. It had no understanding of truth or meaning in any deep sense, but it was breathtaking. Developers built hundreds of applications on top of it. Then, in November 2022, OpenAI launched ChatGPT. Within 5 days, it had 1 million users. Within 2 months, 100 million, the fastest adoption of any consumer technology in history. People asked it to write emails, debug code, explain scientific concepts, plan vacations, compose songs, tutor their children, and counsel them through difficult decisions. The world had changed again. Part 10. The Great Debate. Promise and Peril. With the arrival of powerful AI systems came questions that could no longer be deferred. What happens to jobs? Studies estimated that AI could automate tasks performed by hundreds of millions of workers within a decade or two. Not just factory jobs, knowledge work, legal research, medical diagnosis, financial analysis, journalism, software engineering, creative writing. The economic disruption could be the most sweeping since the Industrial Revolution. What about truth? Systems that can generate convincing text, realistic images, and deepfake videos could flood the information ecosystem with fabrications indistinguishable from reality. Elections could be manipulated, reputations destroyed, history rewritten. What about bias? AI systems trained on historical human data absorb historical human prejudices. Facial recognition systems that worked poorly on darker-skinned faces. Hiring algorithms that discriminated against women. credit scoring systems that penalized minority applicants. When AI makes decisions at scale, its biases affect millions of lives. And deeper still, what about control? As AI systems become more capable, how do we ensure they remain aligned with human values? How do we prevent an AI optimized for a narrow goal from pursuing that goal in ways that harm people? These questions, once the province of science fiction and academic philosophy, had become urgent engineering problems. A new field emerged: AI safety. Researchers at organizations like the Machine Intelligence Research Institute, the Center for Human Compatible AI, and within Google, OpenAI, and Anthropic began working on ways to ensure that AI systems behave as intended, not just in testing environments, but in the messy, adversarial, unpredictable real world. Geoffrey Hinton, the godfather of deep learning, resigned from Google in 2023, saying he wanted to speak freely about the risks of AI. He expressed regret about his life's work, not because it was wrong, but because the technology was advancing faster than humanity's ability to govern it. Yoshua Bengio, another pioneer of deep learning, signed open letters calling for a pause in the development of the most powerful AI systems. Elon Musk, who had co-founded OpenAI, sued the organization he helped create, alleging it had abandoned its founding mission of developing AI for the benefit of humanity. The debate was fierce, honest, and unresolved, and it was the most important conversation of the age. Part 11: Where we stand today and where we are going. Today, artificial intelligence is woven into the fabric of daily life in ways that were unimaginable a generation ago. Your smartphone uses AI to recognize your face, predict your next word, and curate your newsfeed. Your email filters spam with machine learning. The ads you see, the music you hear, the routes you drive, all shaped by algorithms. Doctors use AI to read MRI scans. Scientists use it to fold proteins and discover new drugs. Climate researchers use it to model weather systems of staggering complexity. And the pace is accelerating. Multimodal AI systems can now see, hear, read, and reason across all modalities at once. AI agents can browse the web, write and execute code, and complete multi-step tasks autonomously. Models are being embedded into robots, giving machines the ability to navigate and interact with the physical world. We are, by many accounts, at an inflection point unlike any in the history of technology. Some researchers believe we are approaching artificial general intelligence, a system capable of performing any intellectual task that a human can. Others believe we are still far away, that current systems are sophisticated pattern matchers without genuine understanding, and that true intelligence requires something we have not yet built. But whether AGI is 10 years away, 50 years away, or never, the AI systems of today are already transforming civilization. The question is not whether AI will shape our future. It will. The question is how and who decides. That is the question of our time. Epilogue: A dream become real. From the golden maidens of Hephaestus to the chatbots of our smartphones. From Ada Lovelace's notes on a mechanical engine to the vast neural networks trained on the sum of human knowledge. From Alan Turing's quiet question, can machines think? To the moment when millions of people had their first real conversation with one. The history of artificial intelligence is, at its heart, the history of a dream of understanding intelligence, not just in machines but in ourselves, of reflecting our own minds back to us, strange and shining and full of questions. We have come astonishingly far. We have far further to go, and the most important chapters of this story have not yet been written. Thank you for joining us on World Story Guide. Until next time, keep wondering, keep questioning, and keep your curiosity alive.